Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So, we were talking about yesterday, using this stepwise procedure to try to understand which models are good and which models are bad when you have a response variable and lots of x's. And the game is to try to work out, well, which x's are important and which x's aren't important, all the while the x's are interacting with one another, right? So it's kind of like the x's are like a criminal cartel, and you want to find out which ones are the really bad guys, but they're all bad, right? They're all doing stuff, and they all do stuff with each other, and that really makes it hard, okay? And so multiple regression is really like trying to mess around in the soup of variables and trying to work out which ones are important given that they might be jointly important and stuff like that. So we talked about the idea of fitting every model possible. So you've got a y and you've got a bunch of x's, so fitting every model possible out of that collection, okay, and just comparing those on the basis of some type of not a test, but a comparison between some measure of model fit, okay. So if you've done a regression course, you probably know that if you want to test whether a particular element of a model is significant, you can use a t-test if you just want to test for one variable, or an f-test if you want to test for collections of variables, right? Now, t and f-tests are based on the notion that models are somehow nested, all right? So if I want to do an f-test for a couple of betas in a regression model, then what I'm basically comparing is a model that includes the variables that go with those betas versus a model that doesn't include them. And those models are nested, right? The little one fits inside the big one. And an f-test can be used to compare nested models, okay? What we're doing here is a little bit different because the models aren't nested. When I want to compare the model that has y versus x1 against the model of y versus x2, I don't have some parent model that contains both of them. I've just got this thing versus that thing, okay? And that's why I'm choosing to compare them using this r-squared measure. It's not a perfect measure, but that's why I'm choosing to do that, all right? So yesterday, we talked about using every single possible combination of the x's, but you kind of admit defeat fairly quickly when the number of x's grows beyond about half a dozen, right? I mean, 2 to the power 4 is 16, 2 to the power 6 is 64. And if you're in a position as a data analyst of having to fit 100 or more models, you kind of throw up your hands and you go, I'm just not doing that. There's got to be a better way, okay? And that's how we came to this idea of using stepwise procedures. Procedures that don't fit every model but try to work their way towards the best models. So we ran that yesterday, and the stepwise stuff is in a library called Leaps. Oh, I'm using the wrong mouse, no wonder nothing's working. Okay, and this was the code that we ran. Now what I wanted to show you first up was how you can visualise the output of that particular code. To do that, I need a new library in R, which I'm trying here to install, but it's slow. I don't know what it's doing, sitting there. So I'm just going to wait for that to happen. But in the meantime, let's talk about something else. It's not really something else, it's the same thing, but it's something I wanted to talk to you guys about as part of this broader discussion. So, you might remember yesterday we had a little bit of fun, but then it got all serious when I started to talk about p-values. and how they're ruining everything. So for many years, for probably nearly 100 years in statistics, p-values were all it. And that came from probably the 1920s when Fisher did his work at the Rothamsted field station in the UK. A lot of designed experiments. Now in a designed experiment, Fisher came up with this statement, and I showed you a few weeks ago now, his single paragraph statement which said, if the error is 1 in 20, then I choose to act a certain way. So 1 in 20 is 0.05. And if it's bigger than 1 in 20, then, I act one way, and if it's smaller than 1 in 20, I act the other way. Basically what he said. But he prefaced that with, in a properly designed experiment, and everyone just ignores that bit and goes with, Fisher said 1 in 20, so it must be what we use. And ever since then, everyone's been using 0.05 as the sort of gold standard p-value. But of course, like I told you when we talked about Fisher earlier on, almost all data these days does not come from designed experiments. It all comes from observational studies. So the difference is that in a designed experiment, this variable x that you're going to use to explain this response variable y is generally not so much measured as controlled. So in a field trial, which was the sort of thing Fisher was doing, x might be the amount of water you give a crop or the amount of fertiliser you put on a crop. And you can measure that out pretty damn accurately. And so those x's are, for all intents and purposes, fixed. They're not random, okay? And so you've got the actions of this controlled, not random thing, x, on this random response, y. And there, Fisher said 1 in 20 is the right thing to do. These days, of course, you measure x and you measure y, and x is subject to just as much variation as anything else. It's not controlled. And so Fisher's statement actually doesn't hold anymore, but people still use 0.05. So this has been going on, like I said, for nearly 100 years. Not so long ago, about 4 or 5 years ago, 2014, this paper came out in Nature. So Nature is one of the probably 2 great science journals. There's Science and there's Nature, right? So, you've probably heard of journal impact factors, which are a measure of how, cited journals are. And, so most statistics journals have impact factors of like 1 or something like that, very low. Nature has an impact factor, I think, of about 30, and it's the highest impact factor there is, right? So a lot of people read it. You've probably read it. It looks like a magazine, but there's actually some serious science in there. In 2014, Nature published this article, P-values, the gold standard of statistical validity, are not as reliable as many scientists assume, right? And so there's this article which I've linked on the Interesting Links page, which talks about what is wrong with p equals 0.05, okay? So I'd encourage you to read this. We're not going to read it out loud here today, but I do want you to sort of start to take on board this idea that p-values should not be for you a method that will always work and that you can just rely on inherently to produce the right answer every time, but they should become another tool that you can use. So I'm not saying don't use p-values, I'm just saying treat them the way you treat any tool, right? It's evidence towards some kind of hypothesis, but it's not the hard and fast evidence that people have assumed for 100 years. So have a read of this article, it's really interesting. Look, when this article came out, it was like someone walking into a crowded theatre and yelling fire, right? People went nuts, right? Most of statistics ducked and covered because as a profession, this is what we've been doing for 100 years. And if someone comes in and suddenly says, what you guys have been doing is all wrong, it causes people to get a little bit, what do I do now? Right? So statistics kind of ducked and covered. Some disciplines, the disciplines that rely heavily on 0.05, just shrugged and ignored it. So if you read medical journals and psych journals, they're still doing all this stuff, right? There is one journal that I'm aware of that banned p-values. They won't publish a paper that's got p-values in it. They went and did that, and all the other journals looked at them and waited. And since nothing happened, they didn't follow. So they showed no courage. So we have one courageous journal that's gone and done this. They're out on their own now. Okay? And this is the way that science is so utterly human, right? Because, you know, people have this vision of science as being some kind of inexorable, correct machine that knows the right answers and all that. But at its base, science, of course, is conducted by humans, and there's a whole lot of emotion that goes into that. And so this battle around p-values has become really emotional. So I'd encourage you to have a look at this article. It's really interesting. The other thing I'm going to show you is a really neat... Oh, this is progressing here behind. The other thing that I'm going to show you that is really neat is this article, which is in the American Scientist. That's a picture of Ronald Fisher, by the way. And it's by a couple of statisticians, one of whom is really famous, Andrew Gelman. But I should tell you, this is really interesting. Well, interesting to me, maybe not to you. When I finished my PhD, I finished my PhD here at ANU in 1989. Okay? I know, it's a long time. And you're going, I wasn't born, oh my God, okay. But we'll move past the idea that I'm old and you're not. Okay, we'll move past that. After I finished my PhD, I went to the US and I was looking for jobs, right? And so I was running around different universities applying for different jobs. And every job I applied for was applied for by one other person at least, Andrew Gelman. So Andrew Gelman and I ran into him all the time at interviews. It was kind of a bit awkward, right? Anyway, the good news for me was that I got hired at Stanford, which was awesome, and they didn't give him the job. He got offered jobs that I didn't get offered, which were very good jobs. He's at Columbia University. You know, when you go out on the job market, the employer is taking a bet that you're going to somehow succeed, right? And so you look at Andrew now and me now, and I'm here at ANU, which is fantastic. Andrew's at Columbia still. He's probably one of the best known statisticians on the planet. I'm nobody. That's cool. That's cool. But the bet they took, obviously, they should have bet on him. Anyway. So he's a really smart guy. He is a really smart guy. And a very interesting bloke. He's actually got, I'll tell you this, because you might want to go look there. He's got his own blog site, which is really terrific. It's called andrewgelman.com. It takes a certain kind of chutzpah to, you know, name your website after yourself because, you know, it's pretty cool. And so a lot of his... And he posts there absolutely every day, something different. So he's a really interesting guy. He's got a lot to say about the crisis in statistics and the crisis in science. If you're the slightest bit interested about where the world's headed in these areas, go have a read, okay? I'm a big believer that you should go out and see what's out there rather than just, you know, listen to what I say. Because what I say is mostly right, but it ain't everything. So anyway, he and a co-author, Eric Loken, I think Eric was his PhD student, they came up with this rather nice expression to talk about why the use of p-values and the way testing is done in statistics is misguided. And they called it the Garden of Forking Paths, which is a really kind of curious statement or phrase. And what it means is this. So to people who are in science who use statistics, one of the ways they view statistics is as a pathway from data to discovery. So they have their data. They might have hypotheses and all that sort of stuff underlying their data, but their data is their data. And then on the other end of that process, there's some scientific discovery. And the statistician is the person who guides them along that path from data to discovery, okay? And if you use p-values, you're basically saying that there's a single path between data and discovery, governed by a single number, p is 0.05 or below, and then that tells you whether your discovery is real or not. It's a beautifully simple way of looking at life, right? Unfortunately, like most simple ways of looking at life, it's hopelessly wrong. Life is not simple. Right? Life is hideously complex. You may have noticed, right? So he thought about, well, how do most analyses really proceed? And the answer is, from the moment the statistician gets the data, the statistician starts to make decisions. And these decisions are around what type of model should I fit? How many variables should I include? Are there variables I'm missing? And all these different questions. There's literally hundreds of decisions that are made in every single analysis, okay? And each one has an error associated with it. So he called this the garden of forking paths. You enter at the entrance and you want to leave at the exit, but there is not one single path through that, governed by a single p-value that tells you if you're right or wrong, okay? And of course, as you go along this garden of forking paths, you take wrong turns. And when you take wrong turns, you commit errors, and those errors might compound. And so that number, which is what's the error at the end, might not be just a simple 0.05 based on a single test. It might be an accumulation of errors over literally dozens of decisions and tests that you've done. And so the true error rate is not 0.05 at all. That's just a fantasy. It's some accumulation of all the little errors you've made on the way through, okay? So it's a really nice way to think about this. It's a really complex way to think about it too, and it's a very challenging way to think about it, right? One thing I've discovered about humans in years of interfacing with them, I am human too, but I like to talk to the other humans, is that people love certainty. People crave certainty. Tell me what's going to happen and be right, okay? And yet statistics is all about uncertainty, and what I'm telling you now is it's way more uncertain than even you thought. It's not just do a single test, find the right answer. No way, no how. So this article talks about this garden of forking paths. Really fascinating article, okay, and well worth reading as well. And look, you know, this has very little to do with graphical data analysis, and I get that. And you're sitting here in a GDA class going, why is he talking about this? And the answer is, when you leave university having done a degree that involves statistics, you've got to read this stuff, right? You're not educated if you don't read this stuff. And by that I mean it's great to come out knowing about every F test and every chi-squared test and every T test under the sun. But if you don't know this stuff, you're going to do it wrong in the end. And that's a real problem. So I really would encourage you to read this paper. It's really cool. So have I made that link live yet? I haven't. Let me make that link live. The other one's already live. This is how I have to do things in Wattle. Here we go. Let's go down to that link. Boom, 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 boom. Where is it? All the bits that say hidden from students, there's stuff I'm going to talk about later, huh? Now you can see that one. There you go. All right, has R finished doing what it's going to do in the background? Finally. Okay, we can get back to it. Okay, so what's the upshot of all of this, and why is the point of talking about it? We are going to come up with a model at the end of this process when we do this model selection for our simple problem. You know, 1y, 4 x's, which ones matter? So we're going to come up with a model. Nobody should be under any impression that this model is somehow right, okay? There is no right. There is wrong, but there is no right. There are shades of right. And there's good, better, best, right? But there's no correct, okay? All models are wrong. All models are wrong. So what we're going to embark on is essentially trying to work out which ones are better. All right, so let's go ahead. What's going on? Error in call. Oh, I haven't got Y and X loaded, so let's go ahead. Do that. The problem with lecturing at the ANU, well, one of the problems, apart from the fact that the campus is in rubble, is every time you log in, it's like everything that happened before is gone, you know, so you've got to reload everything, which is why it takes so much damn time. It's very annoying. Okay, so we looked at this yesterday, and we looked very briefly at this table. So, okay, we've got a Y, we've got 4 X's, we're trying to work out which models are good and which models are bad. Here's how we do it. So, column for the intercept, a 1 means that the variable is in, a 0 means it's out. So every model has an intercept, okay? Then we've got all the models that contain x1 or not, x2, x3 and x4. Okay? Then there's a really small gap, and then it tells you the adjusted R squared. Okay? So how do you use this? Here's what you do. Down the bottom, these numbers are going to be big, because big models tend to have big R squareds, okay, and big adjusted R squareds. So what I generally do is I work from the bottom, and I try to pick out the biggest number for the smallest possible model, okay? Now this concept of best explanatory power for smallest model has a name. It's called parsimony, P-A-R-S-I-M-O-N-Y, parsimony. So you've heard the word, it's an English word, parsimonious. So parsimony is the noun that goes with parsimonious. What does it mean? It means maximising one thing while minimising another. All right? So the best way I can explain this is I'll tell you a story. When I worked in the US at the university, we had these guys. There was this little black market in buying textbooks, right? And there were these guys who'd walk around and they'd buy textbooks off academics, and then they'd sell them to students, right? So it was a black market because the publishers hated this. The publishers want the students to buy textbooks off them because they can charge about $400 more, right? But this black market developed. And so these guys were called book buyers. Right? They'd come around to everyone's office. You got any books you want to sell? Oh, yeah. I made some good money those days. I just started out. I didn't have a lot of money, so selling these textbooks was ideal because the companies would send them to you, usually unsolicited, and so you go to your mailbox, there'd be all these bloody books there, and then you're stuck with them. So anyway, this worked really well. So the book buyers came in all kinds of shapes and sizes. One was a terrible human being. He brought his girlfriend with him all the time, and she carried the books. He was this big guy, right? And his girlfriend would be behind, lugging this big bag of books along, and he'd be like, come on, hurry up, hurry up. Oh, my God. I never sold the book to him, because he was an a-hole, right? Anyway. But the book buyer I really liked was a guy by the name of Bill Beebe. That was his real name. He had a business card, Bill Beebe, book buyer. I'm like, that is so alliterative, it's perfect, right? Bill Beebe, the book buyer. And he had a motto. His motto was, and this captures parsimony perfectly, more money, less effort. That was his entire business plan. Buy books off these guys, no effort, sell them for for lots of money. So more money, less effort, right? So how does that work in statistics? More explanatory power, fewer variables. More explanatory power, fewer variables. That's the concept of parsimony, right? More bang for your buck. Okay. So as I run my finger up this page, you'll notice that at the bottom the models are big, at the top the models are small. Okay. So I want to find a smallish model that has a good R squared. So I run my finger up the page, yeah, big, but they're big models. I'm not happy with those. The models are getting smaller, right? This is terrible. This is a model that's got two things in it, but it's only got 42%. But here's a model up here that's got two things in it that gets me 97%. So I run my hand up this until I find the last biggest one, okay? The last biggest one. And, let's be honest, it may be that this one isn't the biggest of them all. It's not, is it? It's not quite the biggest of them all. This one's very slightly bigger, right? 0.9714, 0.9713. So this one is a tiny bit better than this one, but this one here has 1, 2, 3 X's in it, right? So what's the rule? More money, less effort, okay? So I'm getting about the same amount of explanatory power, but I get one whole fewer variables. So this is the one I'd choose, all right? And it's got x1 in it, and it's got x2 in it, and it's ignoring x3 and x4. Now, at the end of yesterday's lecture, someone who I can't visualise right now came up and asked a brilliant question, and the brilliant question was this. When you fit the best one variable model, is that variable that you chose going to be in the model you choose out of the result of a stepwise regression? The answer is no. The best one variable model, we can look here, the best one variable model, so these three lines here, these three lines here represent the best four lines. There's four variables, right? Here we go. Oh my God. I need to go back to mouse school. So those four lines there represent the one variable models, and my choices are 0.657, 0.655, 0.467, 0.217. The best one of those is the top one, 0.657. That contains x3. Okay, the best one variable model contains x3. Okay. The best two variable model is this one here, 0.971. It doesn't contain x3, it contains x2. So if you're using a stepwise procedure, you're not necessarily going to choose the right variable in the first step. It might fall out later. You might say, well, how can that happen? If x3 is so bloody good, how come it leaves when you get the right answer? And the answer is, remember, x2 and x3 are twins. You get one, you might as well have the other. They're not exact twins, but they're close. Okay, so that's what's going on there. So that's how you might use this table. Now look, this is great. This table has 16 lines. It's dead easy for me with 16 things in a table to stand there and run my finger up the page and go, yep, I can pick out the big one, easy, right? But if the number of x's was 5, there'd be 32 lines in the table. If the number of x's was 10, there'd be 1,000 lines in the table. I ain't doing anything with the fingers then. Because, well, it's not even going to fit on the screen. So that's no good. We need a better way to visualise this. So here's how we visualise it. This is in the car library. So I'm going to show you a picture. I'm going to talk about the R that does it. Where is it? Okay. So here's my picture. So what it is, it's a plot of subset size, so number of x's, versus adjusted R squared, and the variables are then listed. So it's basically a plot that shows you what the adjusted R squared is for every model that you fit. Now you'll notice that at the beginning, when you've got relatively small numbers of variables, the R squared's kind of small, right? It rises quickly and it sort of goes up steeply and then it flattens out. So the sweet spot is where it starts to flatten out. So for me, I'm not going to choose a one variable model. The best I can do with a one variable model is about 65%. But with a two variable model, I can get all the way up to 97%. I'm happy with that. So I'm going to choose a two variable model based on this picture. Now, there's something that's not quite right with this picture, which is that, look at that. What the hell is that? Right? That's a lot of different models all crowded on top of one another. So what I'm going to do is I'm going to take this picture and I'm going to zoom into that little slice, right? I'm going to look at this under a microscope. So let's do that. If I zoom into that little slice, so now you'll notice that the y-axis changes from going from roughly 0.2 or 0.1 up to 1 to going from 0.96 up to 0.975. So it's just that little slice at the top, okay? And now I can see more clearly what's going on. Even then, there's still two sitting one on top of the other. I'd have to really slice it thin to see those separately, okay? So that's just showing me the top of the plot. So this is a really good way to visualise what happens when you fit an all subsets regression, okay? You'll notice we haven't yet fit the models using a stepwise procedure. We've used all subsets. I'll show you the stepwise in a minute. But for the moment, this is one way we could go. Now let me just show you the R to produce that plot. And again, I apologise for having to move windows around all the time, but my screen is too small. I need a screen like that one up the back. Yeah, there's a screen back there. Why? Is it so I can see what I'm doing? Well, I got this one. I don't know. Anyway, weird. All right, so what's the R code look like? Okay, so the basic command is simple. The command is subsets, right? And what it does is it takes the output from what Leaps produces. So it takes the output of a stepwise regression, and it looks at each subset model and it plots them with the y-axis being whatever you put here, statistic equals. And here we want adjusted R squared, and the rest is just making sure everything's titled. Okay? So that's the basic code. When I wanted to show you just that top slice, all I do is use y limit being 0.957 up to 0.973. So I just show you only that top slice using y lim. All right? So pretty simple. Now, in case you are interested, and I always encourage people to use the help in R because it's really quite good. So you can get help on the subsets command and it tells you what you need to put in. So object is a reg subsets object produced by the reg subsets function in the leaps package. So in other words, the output of a stepwise regression. And then you've got all these other options. Most of them are pretty boring, but the one you want to look at is this one, statistic. So you've got a choice of what you get it to plot, and there are multiple choices here. We're generally just going to use adjusted R squared, okay? ADJR2, adjusted R squared. There are other measures of model adequacy. They are the Bayes information criterion, so-called BIC. There is Mallow's CP. There is regular R squared, not adjusted. And if you're wondering what is Mallow's CP and what is the BIC, do a class in regression. We have one. You might have already done a class in regression, but you don't remember, right? It was a long time ago. Anyway, these are other things that you can use to compare models. Okay, adjusted R squared is not everything, but we're going to use adjusted R squared here because it's simple. AIC and BIC are the more popular alternatives, but you'll see that subsets does not support AIC, which stands for Kaiki's information criterion. Okay, so that's pretty cool. All right, now I'm going to make the windows go small again. Oh no, I'm not. I'm just going to have another look at the help for reg subsets. This is the command that does the stepwise one. Okay, reg subsets, and what I'm looking for in here is the method. Okay, so we've shown so far exhaustive search. There are other options. There's forward selection, backwards. I call it backwards elimination. They call it backwards selection, or sequential replacement. And you go, but it doesn't tell me what the options are called. That's why, this is something that's always good to know. At the bottom, there's generally some examples in all the help files, okay? But none of them here say methods, so I'm going to have to guess. It should be fun. So let's go ahead and do that. So I'm going to go back here. So this was the one with exhaustive. Okay. So reg subsets, you give it your Y, you give it your X, you give it your data frame, number of models, and instead of method equals exhaustive, I'm going to take a punt here and type forward selection. Okay, let's see how that goes. Warning message. I love R's warnings. In warn.extra rval, model with initial 2 variable was better and is reported. Ooh, I've been reported. Oh my God. Don't worry, I'm not worried. It's because I went n best equals 10 and it wanted to exceed 10, which is fine. Okay, so this is what it does. This is what it does when it uses forward selection. You'll notice this doesn't have 16 lines anymore. It has 1, 2, 3, 4, fits every one variable model. Okay, it chooses one of the variables, then it fits only the 2 variable models that involve that variable. Now you're going, well, there should only be 3 of them. There's 4 of them. That was what the warning message was about. Come back to that in a second. Then it chooses the 3 variable models that involve the first 2 variables chosen. There are 2 of them, and it can fit only one 4 variable model. So in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and we previously fit 15. So we've saved 4, okay? And you're going, oh, gee, it's not much. To which my response is, well, if something costs $15 and someone offers it to you for 11, you're going to take it, right? I mean, it's a discount. And it's small because the problem is small. And if the number of variables was 20, and we're talking about the difference between 2 to the power 20 and a number that's very much smaller than that, then you're going to say, yeah, I'll do that. Okay? And the error message, or the warning message, which has gone off the screen now, said that the model that had variable 2 in it was better than all the others. So that's this guy here. So it's put it in anyway. And the reason it's done that is because when it chose x3 in the first step, forward stepwise then says all my next models have to contain x3, right? And so it goes ahead and it fits the model that has x1 and x3, x2 and x3, what am I missing here? Sorry, that's x2 and x3. Oh, why can't I see? Oh, sorry. I keep ignoring this column because it's so damn close to this one. I'm too close to this. I have to stand back. You know when you stand up really close to something, suddenly you go, oh, what am I looking at? Oh, that's way better. Okay. Now I can't point. I need long arms. What's going on? Someone once called me Inspector Gadget, but I'm not. Damn. Anyway. All right. So 2 variable models. Okay. This one has x1 and x3. This one has x3 and x4. And this one has x2 and x3. So they're all the models, these 3 here, are all the models that have x3 plus one other thing. Now, Stepwise should not have looked at this one because it doesn't contain x3, right? But the error message, but it had a sneaky look. It had a sneaky look. And when it had a sneaky look, it goes, hang on, that's better. So it says, model with initial variable 2 was better and is reported. So it tries to correct its problem. When it gets deep in the algorithm, it's not going to be able to do that, right? Because it has to look at too many models. But I guess in simple problems it does it, and so on. So, again, same process now. You try and pick the model that has the best adjusted R squared based on that. Now, if I go back here and I change to method equals backward, whoops. All right. Okay, it goes ahead and does it. You get the same error message, right? But let's have a look at the output. Come on. Reg out is that. Okay. So when you go backwards, you don't go all the way back, right? So this is the best 4 variable model. Okay, 1 variable comes out, that's variable 4. Okay, so these are all the models that don't involve variable 4. What's this one doing in there? No, what's going on? Okay, these have variable 1. These have variable 3. I don't know what the hell it's done. Am I looking at this straight again? My goodness. Anyway, the idea is it's going backwards, right? Takes things out one at a time and then removes them sequentially. Anyway, I'm not going to embarrass myself by looking at that too closely. I think the third one's called stepwise. No, unknown name. What is it called? No. Sequential, thank you. Sequential. No. Okay, I'll have to go and look that up. I've forgotten. R is big and complex, right? People say to me, how do you remember all this R? I go, I don't. Remember the golden rule in life, of course, right? You remember what you use every damn day, and everything else you forget. That's how life works. So I have for the moment forgotten that. But we'll come back to it later. So this is a way you can run these stepwise regressions. Now, okay, here's a couple of things that you've always got to keep in mind when you're doing stepwise regressions. The first thing is you don't necessarily get the right answer even though the algorithm will give you a single answer. So don't confuse getting one answer with getting the right answer. When you fit an all subsets regression, you get 15 answers and you've got to choose from amongst them in this case, right? You've got to choose the best one out of the 15. The stepwise procedures, they try to identify a single model that's the result of an algorithm in which the best model is chosen at each step and then they build on that. But if it never looks at the best model, in truth, then you're not going to get that as your answer. So even though it gives you a single answer, it may not give you the right answer. Similarly, if you use forward selection, you might get a different answer than if you use backwards selection. Okay? Now here's the best way I can explain this, and it's to go back and look at these pictures again. So remember the plot that we... plots. Remember this plot, we'll go back one. This was the plot of every single model, right, with its R squared, okay? So all subsets regression is the whole plot, right? Every point. Every model that could be fit was fit, the R squared was plotted, okay? What does forward selection try to do? It says, okay, I'm going to choose the best one variable model. I'm going to use that as my jumping off point. So it fits all of these, and then it starts here. And then what it says is, I'm going to only look at models that contain the variable I started with. And so you don't get all of these, you just get some of them. Okay? And what it's trying to do is it's trying to stick near the top. Okay? Because it chose the best one variable model, so it's trying to stick near the top. So the idea is you want to climb this mountain. So think of this as a mountain, you're going up, starting at the bottom, you're going up. You're trying to climb this mountain by climbing from top bit to top bit on each sector, okay? Now, sometimes, you know the way mountains are, to get to the top, you can't always go peak to peak to peak. Sometimes you have to go down and around and then you find another way back up, okay? That might be what the truth is. This algorithm says, I'm going to go from peak to peak to peak to peak and hope for the best. That's what it's trying to do. So, it's carving a path up this mountain with a strategy, peak to peak to peak. Okay, that's forward selection. What does backwards elimination do? Backwards elimination starts at the top of the mountain and it's trying to get down. So it's going trough to trough to trough to trough, right? It's trying to find the fastest way down, descending the most at each step, okay? Now, imagine two people. One's going from the bottom of the mountain trying to get to the top. The other one's going from the top of the mountain trying to get to the bottom. They're using different strategies. This guy's using peak to peak to peak to peak. This guy's using trough to trough to trough to trough. Do they meet in the middle? Not necessarily, right? They can cross. This guy's gone down, this guy's gone up, right? In the middle, this guy might be up here, this guy might be down here. They don't meet in the middle. When they don't meet in the middle, you're going to get different answers, okay? And the reason is because these strategies don't fit every damn model, right? If you don't see every model, how can you know you got the right one? You're just taking a bet that the strategy of going peak to peak will get you to the top. Okay, usually it does, it doesn't always. So if you actually use these different methods, you don't necessarily get the same answer. Now, the data set we're looking at here, you do get the same answer. Pretty simple data set, very simple structure. X1, X2 is the model you end up with in both cases. But there are plenty of data sets where you don't get the same answer coming up as going down. Okay, and that's a problem. So, stepwise procedures are really terrific because in some sense they're automatic, right? They give you a really simple way to get a quick frame on what good models are, but I just encourage you not to take the answer, the single model at the bottom, and say, that's my model, and no other models will be thought about, right? What I think stepwise regression can do for you is it can identify for you a class of good models and a class of not so good models. And then the answer is likely to be one of the better models, not one of the worst ones. But you shouldn't think of it as giving you a single rolled gold answer, all right? Which of course brings... That was good. I like that sound effect. Oh. I wish every time I said something wise there was a ding. And I was like, oh, God noticed. How nice. How nice. It's sort of the opposite of when you do something bad and the lightning comes down and hits you. That's God getting his revenge. Or her revenge. Anyway. Okay. All right. 5 minutes to go. But I want to start talking about something new. Now, normally, what I would do is I would just plough ahead, and after 5 minutes I'd say, remember where I got to. And I know how unsatisfying that is. So I'm going to encourage you guys to spend the next 5 minutes doing something fun instead. So we're going to finish there. You guys can go and enjoy the beautiful sunshine outside. Because rather than start something new that I can't finish, I'm going to exercise some self-control for a change. So there you go. So tomorrow we'll talk about some different techniques for regression. Alrighty. Let's move away from the microphone because I think it's still recording. One time after lectures when I finished early, everything got recorded. That's no good for anybody, is it? So that's